actually. Aristotle thought light came from your eyes, hit the object, and came back, sort of like radar. But this fails to explain some phenomena. You know, like when it's dark outside. This video will be part of a two-part series. This video will explain the classical mechanics of light, and then the next video will explain the quantum mechanics. In order to fully understand what light is, we need to develop an understanding for waves and how they're described mathematically. But don't leave. I know some of you have equation anxiety, but I promise I'll be gentle. Light is electromagnetic radiation. It's the electric field and the magnetic field interweaving and dancing parallel to each other. The way we describe this mathematically is using vectors. Vectors are basically arrows in space. And so you can see this. And you can see this guy has an x part of 3, a y part of 3. And if you look at it, it forms a right triangle, and whose hypotenuse you can figure out, and that'll be the length of the arrow. We write vectors using this notation. We write them in order of axis, so the x, the y, and the z, if you want, to be in 3 dimensions. You can add vectors, and now I'm going to add 2 vectors together. So let's say I have a vector with the simplest possible case. I have a vector, one of the simplest possible cases. A vector that's 3 and 3, and a vector that's 2 and 2. Well, how you add vectors in column form is you add together each of the things, kind of like this. So this would be 3 plus 2, and it would have a y that's also 3 plus 2. So this gives us so adding these 2 vectors together give us the vector 5, 5. You can see that if you look at this, you can see this is what you would get if you put this vector right on top of this vector. You would get the vector 5, 5, which, by the way, happens to have, no, that's 5, 4, 5, 5. But the electric field oscillates, so we're not going to describe it using a very simple vector. We're going to use cosine of t, where t here is time, and we're going to have 0 y component. The reason we use a cosine function is that if you've ever graphed a cosine function, it goes up and down, up and down, up and down. And we can use this to represent oscillation, as cosine itself oscillates between up and down, up and down. Cosine of f of t. As you can see there, with the horizontal component of 0. The reason we compose this little f of t function in there is because it could be in literally anywhere in its wave value. It could be here or here. This will tell us what the time is. Now we're going to add a new term, phi, or phi, if you want. This will tell us how far along in its cosine function it is. It could be here or it could be here. This will tell us where to start. So now our function looks something along the lines of cosine of f of t times phi with its y coordinate of 0. This little electric field will go back and forth, back and forth, back and forth along the x-axis. What happens if we start changing this y coordinate? Especially, what happens if we flip it around? So this time it has an x coordinate of 0 and a y coordinate of this. Then what happens is you get vertically polarized light. Light that's been shifted 90 degrees from where it is. So instead of electric field, magnetic field, it's now magnetic field, electric field. Instead of y being magnetic and x being electric, they flip. And what happens if you make it trace out a circle? If you make your vector trace out a circle, it is do that, and that, then that. You get a spiral-looking staircase effect. And we call this vertically polarized light. We can add our super complicated vectors too. If we have a horizontally polarized electric field vector and a vertically polarized electric field vector, and we add them together, we get a diagonally polarized vector. And this sum of these two vectors has a special name, a superposition. Now, how do polarized filters work? Well, a polarized filter will, let's say horizontally polarized, will absorb all of the energy going towards it, all of the light energy going towards it horizontally. This is why, if I have a photon that's, say, diagonally polarized, it's the superposition of two others. And I put it through a diagonal filter, it loses half its energy. If I put it through a horizontally polarized filter, it loses half its energy and gets turned into a vector that's now vertically polarized. So vertically polarized photons light rays will go through fine. Diagonal ones will lose half their energy, and horizontally polarized ones won't go through at all. This is why if I have one polarizing filter and I take another and orient it exactly 90 degrees off, no light comes through. Because the first filter, will take the horizontal energy, and the second one will take the vertical energy. So overall, no light makes it through. But kind of weirdly, if I take one, set the second filter like this, and then set a third filter like that, some light will actually make it through. How is this possible? Well, the first filter will take away the first filter takes away the vertical aspect of our vector, so now our vector is moved to this. Then this moves it back up to here, and then it gets canceled. The reason you heard me say change it up is because that's not actually wrong. It's just a separate basis vector. It's just we're changing the basis from this to this. We're slanting the XY grid. Hey, thanks for watching that video about light. If you liked it, go over to my YouTube channel, hit like the video, subscribe it, and share it with all your friends.